This is a sketch of the instrument known as a mass spectrometer. Remember, this is not the actual instrument. We use it in order to separate things that are very small and that have minute differences in mass. So essentially, it's a curved tube, and at the point of inflection, you have a magnetic field. You inject a sample over here on this side. As the sample enters the chamber, we knock off the electrons, so all we're left with are nuclei, that is, positively charged, and they are then passed through an electrical field which causes them to accelerate towards the region where the magnet is. Now, we know from physics that a moving charged particle will interact with a magnetic field. Now, the level of interaction is going to depend on the charge to mass ratio of these particles. Most of these particles have the same charge. They're all basically the same number of protons. What is different is the number of neutrons. So it really is the mass that is different. And so depending on the number of neutrons in each one of these atoms, you're going to have a different level of curving here. So like, for example, if I'm taking a curve at 20 miles per hour with my Honda Civic, I can probably make a very sharp turn. It's a small car. If I try to do that with an 18-wheeler, yeah, I mean, it's 20 miles per hour, but that's a big truck. So it'll probably have a wider turn, not be able to negotiate the curve as easily as I can with my Honda Civic. In the same way, the nuclei that are smaller will make a sharper turn. The nuclei that are larger will make a wider turn. So by the time they emerge from the effect of the magnet, basically each one of these streams of particles has been separated according to the mass to charge ratio, but mainly the mass. And what's going to happen is they're going to land at a detector that is going to register both the position where the particles hit and also the intensity of each one of those spots, which can be converted into the percent of each particle. So in this case, we put a sample which was neon gas, and we have three major isotopes of neon: neon 20, neon 21, neon 22. Since neon 20 is the lightest one, has less neutrons, it makes a sharper turn, and so it is found in this position here, which calibrated, we can determine which isotope it is. Now, what's interesting is that according to the intensity of the spot, you can determine what is the percent of each. And you can see in this chart over here that neon 20 makes about 90.5% of the whole sample. So any sample of neon that you would take is going to have these three isotopes, and 90.5% of the atoms are going to be the neon 20 isotope, and then you have the other two here. And so this is how scientists determine what is the distribution of isotopes of any element, as long as they have a very pure sample. Now here's where it gets interesting. Silver occurs as a mixture of two isotopes, silver 107 and silver 109, and running a sample of silver through the mass spectrometer gives us these results of the abundance of each isotope, 107 and 109, and the actual calculated atomic mass in atomic mass units. Now, you might remember a table like this one that shows us what is the actual mass of each one of the subatomic particles. And you can see here that the proton and the neutron are roughly about 1 AMU, but they differ a little bit. The neutron is slightly heavier. So the question is the following. Silver 107, atomic number 47, would have 47 protons and 60 neutrons. Now, based on this table here below, right, based on these numbers here, the mass of a silver atom should be, a silver 107 atom should be 47 times the mass of the protons plus 60 times the mass of a neutron, and it gives you 107.86129 AMUs. Oh, wait a minute. That's not what it says here. It says that a silver 107 atom has a mass of 106.9051 AMUs. In other words, why is it less? Why is the actual atom lighter than the sum of its parts? Now, you could argue things like, well, it's just a matter of the error in the instrument. No, no, no. This is not the error in the instrument. As you can see, we're dealing with things that go all the way to 4 and 5 decimal places. This is highly precise and very accurate because of the calibration. So, with that in mind, let's discuss what is happening here. Why is it that these guys are different? All right. So let me come here. Let's see it. I'm going to take this guy out of here. Okay. So we're going to define what is called the nuclear binding energy. This is the energy required to break up a nucleus into its component protons and neutrons. If I took an atom, actually specifically a nucleus, and I were to put enough energy to break up all of that strong nuclear force interaction that's in there, the amount of energy required would be the nuclear binding energy. So let's pretend that we're going to build an atom of fluorine, specifically fluorine 19. Well, one way we could think about it is if I were to break that thing up by applying the nuclear binding energy, I could say I could get 10 neutrons, right? And essentially 9 protons and 9 electrons. So I'm going to represent that as if when I made the actual atom of fluorine 19, I took 9 atoms of hydrogen and I added 10 neutrons to them. Okay, that is the proposal we're making here. Again, this is just, we're just proposing this. This is kind of like a fake, but I don't know that fluorine 19 is made that way, but we're going to make it that way. According to our standard law of conservation of mass, if I add up the mass of 9 atoms of hydrogen, protons plus electrons, and actually, if I wanted to, I could probably drop the electrons because electrons are like 1800 times less massive, so it wouldn't even register here. But if I take that and I add 10 neutrons, I should get the same mass as an atom of fluorine 19. Okay? Pause the video if you need to make sure you understand what I'm saying here. Okay? I'm just pretending that I'm going to build a fluorine 19 atom from scratch. So the question is that the case? Well, let's do the calculation. 9 atoms of hydrogen at 1.007825 AMUs. And, like I said, maybe we are considering, you can consider just the protons if you want. And then we're going to have 10 times the mass of a neutron, which is 1.00866665. 1.008665, I'm sorry. And when I add that up, I get 19.157075 atomic mass units. Versus what is the actual measured atomic mass of an F19 atom? Well, according to the mass spectrometer data, it's 18.9984 AMUs. So we have a problem, right? Conservation of mass says that it should be the same, but it seems like it isn't. If we calculate the difference in mass here, delta M, so we subtract the actual mass minus what it should have been, and we have a deficit here. This deficit, minus 0.1587 AMUs, is what we call the mass defect. And this is the same situation that I presented earlier about the silver 107 atoms. Every time that you do these calculations for any atom, you end up with this mass defect. It's as if somehow the law of conservation of mass got violated. It was not obeyed here. We lost mass. Now, in the 20th century, Albert Einstein came up and said, you know what happens? At this level of matter, mass and energy are actually interconvertible. In other words, the so-called mass defect is not a loss of mass, it's a conversion of mass into energy according to the famous equation delta E equals mc squared, where mass, in this case, we're going to say, well, what is the mass defect? The mass that we seem to have lost. So let's do the calculations here, okay? In order to convert this to energy in the appropriate units, we're going to have to convert the mass defect from AMUs into kilograms, and I'll show you why in the next slide. So let's do that conversion. So 1 kilogram is essentially 6.022 times 10 to the 26 atomic mass units. Remember, 1 gram is an Avogadro's number of atomic mass units, but this is a kilogram. So we're going to put that in there, and we get negative 2.635 times 10 to the negative 28 kilograms. The reason why I did this is because when we look at the equation here from Einstein, we're going to get kilograms times meters per second squared. And that's important because, as we will see, if we remember the units of energy, a kilogram times meters squared per second squared is 1 joule of energy. That is a conversion that we've used in the past. So we can now convert this amount that we had here in kilograms, the mass defect, right, that we calculated here, this mass defect, times the speed of light squared, and we get minus 2.37 times 10 to the negative 11 joules of energy. Now, this is for one atom, right? Because that's what we calculated. We don't normally in chemistry work with single atoms. We work with moles, remember? So let's go ahead and convert this. Minus 2.37 times 10 to the negative 11 joules per atom. Let's multiply that times Avogadro's number of atoms per mole, and we obtain negative 1.43 times 10 to the 13 joules per mole. Or, in more familiar terms, minus 1.43 times 10 to the 10 kilojoules per mole. Now, why is that meaningful? Well, tell you what, the major thing that is happening in this process, this is negative. In other words, this is energy being released as this atom, as this nucleus is being formed from essentially mixing in, protons and neutrons, right? So this is the process that is releasing this kind of energy. We're talking a lot of energy. Ordinary chemical reactions typically have enthalpies in the hundreds to 1000s range. For example, the combustion of octane, which is the energy that is used to power our combustion vehicles, is on the order of like minus 5,000 kilojoules per mole. You're talking several orders of magnitude, much less than what we're expressing here. In other words, the formation of these atoms would release a tremendous amount of energy, or from the other perspective, it would take a lot of energy to break up an atom of fluorine. So we're going to call this the nuclear binding energy, 1.43 times 10 to the 10th kilojoules per mole, the amount of energy that would be required to break up a mole of fluorine-19 atoms into their component subatomic particles. Now, the problem is that we would like to devise a way of being able to compare some isotopes to others and some nuclides to others, some elements to others, And this is very specific for fluorine. So what we do is we're going to define what's called the binding energy per nucleon. Remember, in our language, in our jargon here, a nucleon is one of the subatomic particles in the nucleus, either a proton or a neutron. So what we'll do is we'll take the binding energy and divide it by the number of nucleons. So in this case, fluorine 19 has 19 nucleons, right? Protons plus 9 protons plus 10 neutrons. And so this gives us a value which would be 1.25 times 10 to the negative 12 joules per nucleon. And since now we have something that is based on a nuclear subatomic particle, now we can use this to compare, well, what is the binding energy per nucleon for other isotopes? And we can generate the following chart. We're going to plot the nuclear binding energy per nucleon versus the mass number. And we get this here. This is the graph that is generated in this process, right? So what does this tell us? Well, it tells us that essentially for very small mass numbers, we have very small nuclear binding energies, right? And then as you increase the mass number, you start increasing nuclear binding. Remember, the more nuclear binding energy per nucleon you have, the more energy it takes to break up that particular nucleus, or in other words, the more stable that nucleus is. Notice that it increases and it peaks somewhere around iron 56, after which it starts kind of dropping off, right? Notice that? So again, remember, the higher the ratio of nuclear binding energy per versus the mass number, the more energy is required to put in to break it into individual particles, and therefore the stronger the attractions in the nucleus, the more stable it is. So notice that elements with mass numbers between 40 to about 100 are the ones that are most stable, with iron 56 being the most stable of them all. That's very interesting, and maybe at some point you can look this up, but there is a significance when astronomers study stars and other celestial bodies with different spectroscopic techniques. One of the things that they analyze is for the presence of iron 56. And because processes in nature are going to tend to either build up towards that from a lower nuclear binding energy, or from either by reducing the size of the atom or by increasing it. These are the processes of fission and fusion that happen in the stars. Again, I'm not an expert, I'm not an astronomer, I'm not an astrophysicist, but it's a cool topic and I encourage you to read about it sometime. Okay, so let's go ahead and we'll pause here. And in our next section, we'll talk about some of the applications of radioactive isotopes.